If y'all love elementary school math, this is the video for you because we're basically doing that. This video is really all about adding, subtracting, multiplying, and dividing. But instead of doing it with numbers, now we're going to do it with sets. And what this is actually called is set algebra. Okay? So we got some fun stuff. That's what we're doing, adding, subtracting. Maybe we can play with fun colors as well. It is a kindergarten day, but a little bit more complicated. It's like college kindergarten. Nope, that's not true. Anyway, let's teach this with an example. Let A be the set of my usual pizza toppings. So let's say pepperoni and Parmesan. Does that count? Cholula. I think that's how you spell Cholula, the hot sauce. And pineapple is a good pizza. And then B be the set of my girlfriend's pizza toppings. Let's say she puts on pineapple. I actually don't remember all the things she puts on it. Yeah, she puts on more stuff than this. I think she also puts Parmesan. Oh, we have to we got to make this more interesting though. It needs something that I don't put on mine all the time. I didn't think this one through. I just make something up. You all won't know. And what are the chances that she watches this video? I don't know. Let's say pecans. Gonna make her sound great, ridiculous. Pretend she likes pecans on her pizza. All right, let's do some set operations. Don't tell her, okay? All right, and then let's have omega equal the set of all pizza toppings. All right, it'll be our domain of discourse. What does all pizza toppings mean? Don't worry about it. Just assume for the purposes of this math that that's what omega is referring to. So let's give you some questions. All right. What I'm going to do is I'm just going to kind of introduce each set operation in the context of pizza toppings. So each one of these is going to be a little definition. We'll start with union. Okay, so union is like adding. All right, it's like taking stuff from both sets and adding them together. All right, so this is, think of it as adding. So A union B just takes the things from both sets. Takes elements from both sets. So we take all the things in A and all the things in B and put them in one set. So it's going to be the set, I'm going to start abbreviating, pepperoni, Parmesan, Cholula, pineapple, right? It takes the things from both sets. Now, we're not going to add pineapple again because remember, one of the differences between sets and arrays is that sets don't have duplicates. So we already added pineapple. We already added Parmesan cheese. The only thing we need to add is pecans. That's the set union. It just takes everything from both sets and puts them into a single set. But again, remember, sets don't have duplicates. All right, and that's unions. That's basically addition. The next one, let's talk about intersection, which is actually not really like subtraction, but intersection. A good way to think of union also, and I should have maybe written this down, union is like the word or. We need everything from one set or the other set. All right, but intersection, that's like the word and. What is in the first set and the other set? So here, what's their overlap? Okay, so you can have intersection as overlap as well. It's the overlap, it's what's in both. This is what's in either. So that's kind of the difference between intersection and union. And they basically look the same, just upside down. So what is in both sets here? Well, we don't both like pepperoni. She doesn't really like pepperoni. We both like Parmesan. We both like pineapple. So yeah, that's the intersection. It's a set containing Parmesan and pineapple. And that's basically what intersection and unions are. Intersection, what's in either. Intersection, what's in both. Union, if you think about Venn diagrams, right? Then intersection is going to be this red part. And union will be, well, everything inside both circles, right? Okay, let's go letter C. Just to introduce some more things. We have two kinds of complements here. We'll start with a partial complement, like your outfit looks kind of good. Actually, it's a different kind of complement. They're spelled differently. So complement with an E is different from like saying you actually, do have a nice looking outfit. Complement is like complementary colors and stuff like that. So the partial complement, that is like what is in A, but not B. It's subtraction, basically. Okay? And what it does is it takes all the elements in A, and then we remove the elements that are also in B. Okay? So the elements in A we take out the elements that are also in B. Okay, so that's why it's like A minus B. We start with A, and we get rid of everything that's in B. And there's a couple of different ways of writing this as well. I've seen it written with a slash, like a forward slash, kind of like a fraction as well, but this is the notation the book uses. So here we just take everything that's in A, and we subtract out what's also in B, already color-coded. So we're subtracting out Parmesan, we're subtracting out pineapple. We don't need to subtract out pecans, because pecans were never in there to begin with. So it'll just be pepperoni and Cholula that's left once we take A and we subtract out B. Once we look at the partial complement. Okay? So it's just pepperoni and Cholula. In other words, what does Jason like on his pizza that Kendra does not also want on her pizza? Okay, so if we have a partial complement, you might be thinking, what other complements are there? Well, I've got the answer ready for you. The total complement. And that also has a ton of different notations. You might see this as A bar. You might also see it as like, I'm not going to keep these. You might see it as A complement. You might see it as A prime. I think there are some other ways of writing it as well, but we're going to be writing it with A bar here. But you may have also seen the complement, I think is the most common second thing. Okay, and that's just shorthand, really. Really what A bar is omega minus A. So it's everything that's not in the set A. So it's shorthand, right? Because we don't write the omega. This is like a subtraction sign. And then the A is right there. So this is everything that is not in the set A. So here, what is A bar? Well, A bar is a lot of things. A bar is anchovies. A bar is ham. A bar is green peppers, etc. Everything, single pizza topping that you can think of, that's not one of these, is in this set. This is a big set, right? The size of the set up here is 2. size of this set up here, that is a big set because omega is a big set. The domain of discourse is often a very big set. All right. Okay. So we're going to finish. We got one more operation left. It's a bit of a weird one. All right. And we're going to go on a new page just for letter E. It's called the Cartesian product. You may have heard the word Cartesian before. You may not have heard the word Cartesian before, but the Cartesian product has to do, it's basically creating ordered pairs. So what we'll do is we'll write A times B, just a multiplication sign. And it's every possible ordered pair between A and B. Like essentially A is our X and B is our Y. So with A first and B second. So what is this going to look like? I'm going to write it over here so we have a little bit more room because these oftentimes take forever to write. So it's every possible ordered pair. So we'll write ordered pairs like this. What's the first possible ordered pair? Well, could be pepperoni and pineapple. We take the first element from A, the second element from B. Pepperoni, pineapple. We'll give more examples of this in the next video as well. What's the second ordered pair? Well, pepperoni could also go with Parmesan cheese. And I say second ordered pair, remember that sets don't have order. It's just the easiest way to write them down is to go, in a very structured order. So we also have the ordered pair, pepperoni and Parmesan. I'll write down one more. All right, we also have, pepperoni and pecans. That's another ordered pair. And then we could keep going, right? We could do Parmesan and pineapple. Which we haven't written down. All right, and so on, right? It just goes forever. Every combination where the first is an A and the second's an B. So how many elements are there going to be here? This is where the notation comes in handy. There's a lot, but there's not infinite. There's 12. Because there are 4 different A's, and each A element has to go with each of the B elements. So there are 4 that each have to go with 3. That's going to be 12 total. So it will always be their sizes multiplied, which in this case is 12. I believe there's a math theorem that says that. 99% sure. If that's not the case, you find it, you let me know, I'll give you some extra credit. All right, so that's pretty much it for Cartesian product. We'll do more practice with Cartesian product in the next one. I think that's kind of the main weird one. A last little example of something that you may have seen before is this guy, the set of all real numbers. We can visualize with a number line, right? Do that all the time in math class. Oh my gosh, that is not the nicest number line I've ever drawn. Well, what is R cross R? R cross R is a set of all real numbers made as an ordered pair with all real numbers. Well, what's the list of all the ordered pairs where the first number is a real number and the second number is a real number? Well, we call it R2. And what it looks like, you may have seen this before. This is what it looks like. This is just a set of all real numbers on the Cartesian plane is what it's called, the Cartesian plane, right? And so it's just, real numbers going in the X direction and the real numbers going in the Y direction, and we make them in ordered pairs, any combination. If this looked familiar, that's probably why. Okay, the Cartesian plane is a Cartesian product of R and R. Okay, and you get some really interesting things when you go further than this, right? There's R3, there's R4, there's R5. You can do this with Z2, you can do this with Z3 for all the integers and stuff like that. Those are called lattices. I'm getting excited, but the point is, right, is a set of all ordered pairs of real numbers is just a Cartesian product. So we've done this before. Let me know if you have any questions. The next video is just for more examples, just to get some extra practice, okay? Because this video was long, but I wanted to give some extra examples, but I don't want to do it all in this video. We're long enough. Anyway, enjoy. Have a good rest of your day.